do at the screen? All right, any questions before I get going with the next segment? All right, I'm eager to get going because there's a lot of things that I want to cover to make sure we're all ready for the next homework, which, by the way, is posted. Yeah, there is no let-up. I'm sorry. The good news will be there'll be no homework in the week of the midterm, and that's the bad news, is the week after next. Let me try to get this guy out of the way for now. All right, so we're going to be talking a little bit about, not just a little bit, but quite a bit about user interfaces for the next several weeks. So the entire idea is that when we get to these design patterns, that the design patterns are a lot more memorable when you have something visual, as user interfaces give us something visual. And I remember at the first day of class, someone said, I heard that we have to learn Swing in this class, and no one uses Swing anymore. And so I'm very sympathetic to that point of view, because that is the truth, right? I mean, who uses Swing anymore? For that matter, who writes user interfaces on a desktop client anymore? You know, there are a few people here and there, but it's pretty rare. I mean, these days when you make a user interface, you're probably going to write that user interface in JavaScript. And so I could do that and show you how to write user interfaces in JavaScript, but it's harder to see these design patterns in JavaScript than it is to see them in Java. I was thinking, maybe I should switch to JavaFX. And so I gave it a good try, and I looked what the equivalents of the Swing patterns would be in JavaFX. And we're actually going to do a little bit about that as a cautionary tale on how a toolkit looks like when it's designed by people who don't know what they're doing. So there are quite a few things in JavaFX where you say, oh my God, these people must have been maybe from the computer engineering department or somewhere where they don't have a course in design. I'm kidding, I have no idea what they do in the computer engineering department. So, so the beauty of Swing in a way is that it was designed right at the time when people were just getting very excited about design patterns, and everyone read up a lot about it, and so people were really on top of it, maybe more than they necessarily are today. So there are a lot of good examples on how to do things right. And so I'm going to show you enough Swing to be dangerous, but not enough for actually production code. And I will show you a bit of then how that looks in JavaFX and how that looks in Android. And for your project, you can perfectly well choose which of those toolkits you want to know. I mean, it makes perfect sense for me to say, how much marketing value am I going to get out of a Swing project, and instead I'm just going to use something else. That's just fine with me. But for teaching the basics, Swing is oddly enough still hard to beat. So the other thing is, since someone asked me, what about those projects? So we're going to have to plod along a little bit longer before we can get going with the project. I would say it's about a week or two after the midterm that we're going to get going with organizing. So the entire idea is it's supposed to be a 1 month project, but 1 month projects are scary because the month is over faster than you can think. So I would like to ramp us up slowly so that the teams get to know each other and that kind of stuff. But we're not quite ready yet. So it's not a humongous project. It's meant to be the first team project in your class. So don't get overexcited about it. You're not going to reinvent the world. All right, so on to basic Swing. So you may have seen this or not. A lot of Swing programming really is copy and paste, that there is certain procedures, a certain ceremony that you have to do trivial things. So as a case in point, you want to put up a window, just a window with stuff in it. And then you have to make a new JFrame. You have to call crazy things like set default close operation and set visible or true. Those are all great indications of not so wonderful API design. If you have to write the same code over and over again, then that means that someone there, really could have given the API an extra spin. But that's the way it often goes. So I'm not even going to explain what these things are. I'm going to assume that you are professionals, meaning that you can copy and paste the stuff with wild abandon without having to understand everything. If you have questions about it, I can drone on forever. But I'm just telling you that's the magic that you need to get a frame to appear. To add components, there are multiple ways of doing it, and so the way that I'm showing you here is one that is simple and effective for a week or so. So you make buttons by saying, here's a button, construct it, and by itself, it doesn't show up anywhere. You have to add it to the frame. The way you add it to the frame is by calling the add method, but by default, again, for no other reason than bad API design, by default, the frame has what's called a layout manager, that when you add one thing, and then you add another, and then you add another, then they just get put on top of each other. Not very smart. And so if we want to have them put next to each other, we have to tell the frame to use what's called the flow layout. They could have easily made the flow layout the detail to save us this little step, but they never really thought about making the simple program simple. So let me just show you this program and run it, because that'll be much easier than going through all of the steps. Let's see if I have it here. Nope. Let's see how much of this split screen shows. Good. All right, so yeah, let me run it first so that's less abstract. Here it is. Notice that the buttons look different because this is running on the Mac with the Mac look and feel. So I have to say hello button, a say goodbye button, and a text field here that says click a button. So if we go through the layout here really quick, you see how the hello and goodbye button are done. We have the text field here. We do this flow layout thing so that when add works, that they get added next to each other, and you just add them, and the flow layout makes it go longer and longer. Actually, I still have the window open. It should be here. Oh, here it is. It's called flow layout because they kind of go with the flow. If I resize the window, you see that it just wraps them just like words in a word processor. May not be the most professional layout, but it'll be good enough for us for the next week or two. Later we'll use what's called the strategy pattern to learn how to change the layouts. And that's all there is to it. Over here you see a few lines of that stuff that you always need to do with the set default close operation and the path that you should just copy and paste. So that's all this program did. It put up this frame. Yeah. I type PACK and then the two parentheses. PACK. And then two parentheses and then a semicolon.
Oh, yeah.
That's what I do.
I mean, what kind of things it does?
Okay. So I will tell you, but before telling you, everyone else, who right now wants to take this time to check their Facebook status, this would be a really good time to do that. So what Pack does is it makes the frame size just small enough to hold all of the user interface components. So it shrinks it down to the minimum size that's required.
So we can also set a fixed size for it.
You could also set a fixed size if you wanted to, and I don't really care, but this is called Pack right now. So when you look at the documentations of these toolkits, Swing or JavaFX, you'll find that each of those classes have a humongous amount of things that you can do. Let me just pull that up. So let's just look at the JFrame. And then here it goes and explains, first of all, how to use it. And then you have, maybe a couple dozen methods here for JFrame. Then you're inheriting about 50 methods from window, about 150 methods from component. And so there's no hope for a mere mortal to understand what all of these methods do. And so I'm not going to be able to tell you in minute detail what they do, even though having had to document quite a bit of this in one of the Java books that I wrote, I probably know quite a few of them. But most of them you don't really need for every day. So the reason I use Pack here instead of set size is it's shorter. And it does the job. So right now we're not after pretty user interfaces, but just after something that gets the job done. Same thing with set default close operation. So you would think that when someone closes a frame that it would also close the program, but the default is that the program keeps running, which is a little inconvenient. And by setting this option here, one says, I actually want to terminate. And that makes some amount of sense that that's not the default, because if you write a word processor, and as soon as the user closes the window, everything is gone, that might not be so smart. On the other hand, you would think that someone who writes a word processor would also be smart enough to override on close to save the work or some such thing. So anyway, that's just the way it is. One can quibble with these minor details. So what I really want to show is how to make these things do something interesting. And so let me do that by negative example. So right now I'm going to click on the Say Goodbye button. Watch carefully what happens. What happened? Nothing, right? So it blinked and that was it. And when you look at the program, it's clear that nothing could have possibly happened because there are no actions associated with it. Oops. Oh yeah. So when Swing was first designed, the idea was that the way to get actions to happen is you would add what's called listener objects to the button. So a listener object is an object that belongs to some class that implements the action listener interface. And so here's the action listener interface as a single abstract method called action hook 1. You would make somehow, and we're going to make one by hand in a minute, one of these objects, attach it to the button, and then whenever the button was clicked, the logic that handled the mouse action would then notify all of the action listeners. We will later come back to this. It's an important design pattern, but right now we're just going to see how it works in this instance. So in the olden days, and the book goes through that in some detail, the way you would do that is you would make a class that implements action listener. You would make an object of that class, and then you would hand that object to that class to the button. Now here we are 15 years later, and finally we have Lambda expressions, so we don't have to do any of that. So nowadays, it is much easier to do this than it ever was. So if you ever learn how to do this the hard way, you'll really like the new way, and if you see the new way, you'll never want to know the hard way. So now all you have to do is you add a lambda expression to add action listener. Because the action performed method takes a parameter called event, you do have to put an event here. We almost never use it. There's nothing really interesting in this event. There is like the event source. Well, hey, I know what the event source is. It is the button, because I'm attaching it to the button. And is there anything else interesting in it? I think there may be a timestamp in there. But, it's easy enough for me to find out what time it is. I can just call instant of now, and I know what time it is. Later when we deal with mouse events, we'll look at the event, because mouse events tell me where the mouse was clicked, the X and Y of where the mouse was. But that's a few weeks down the road. So right now, we still have to mention the event. You can call it E if you like, but that's spell it out anyway. And afterwards, you put the button action. If the button action fits into a single expression like here, you just put the expression. If you have more than one expression, you have to put braces around it. So in this case, we set the text of the text field to hello world. Let's see where I have the code for that. Yep. Okay, no. I understand your question, but let me take that apart slowly. Let's see if my nifty pen works. I need to calibrate it. Let's see if I can do this. Gosh, the thing's driving me crazy. I'm sorry. Still have much to learn. One more try. Yeah. Okay, it's not going to happen. Okay, we'll just do it by hand. So, what did just happen? So your question was, what does the event here mean? Can you say the question again? Because say the question again. What did you think it was?
This is
Okay, so the short answer is no. So let me take this apart, and so this is hello button. Alright, so here's this thing. And so now I'm going to write out what it is that's actually going on. So it looks like here that as if I'm passing this lambda expression to this add action listener. Let's first of all remember, what does add action listener want? It wants an object of type action listener. so what this really means is that I have an action listener, and I'll call it Al, and that is now set to something, and then what really gets passed here is Al. So now what is Al? Al is an object of some class. Of which class? Well, it can't be a class action listener because action listener is not a class, it's an interface. So it is some class whose name I don't know, and it's some synthesized class, and I'll give it a name. So there's some, let's call it action listener $1, 2, 3, 4, that is synthesized on our behalf. That is a class, not a public class for sure. It implements action listener. It has a single method called action event. So public, action perform. Action perform. It takes a parameter of type action event. That parameter is called event. And then it executes text field.send text. So you can see the advantage of using the lambda expression is you only need to type the blue stuff and all of the green stuff you get from it.
So will the compiler replace that?
Oh yes, the compiler is going to get busy and synthesize this class. It really does that. Yeah, so the compiler makes this class behind your back and gives it some name. You could find out what that name is if you were to do this not with action listener where you don't have control, but if you do this like in your own interface, do it with a comparator. In a comparator, you can, because you write the comparator, you can do anything what you want. Just do a system.out.println on the comparator object. It'll print the name of the class, and it'll be something mumbo jumbo. And that way you can see it really does make an object of some class that you don't have control over. So, but of course, when you think about it, you don't really want to think about it, except, for everyday point of life, you write a button listener. What do you want to know? You want to say, how do I specify what should happen when the button gets clicked? Well, all you do is you write in here what you want to have happen. And you have the event and the arrow. That one is still a little bit of fluff that you need, right? But it's supernatural, I find. When the hello button is clicked, then call this thing. So there's just one little wrinkle about that, and that is this text field thing here. Notice that the text field is not declared inside this thing. The text field is declared somewhere out here. Now you might say, so what? That looks close enough. But now look at the actual code that happens here. This class action listener does not sit inside any other class. It's just a regular old class. How can it access the text field? Well, but there are no inner classes in the virtual machine. The inner class is a syntactical convenience for us. The virtual machine only has top-level classes.
You mean which one access?
What's that?
From the listener access the text field?
Well, so this method here changes this text field, but the text field is nowhere in scope. If you wrote this class by hand, it wouldn't compile. So there's actually some more magic going on. So I'll write that magic in red. That actually, what happens when this class gets synthesized, it gets an instance variable. For every value that is being touched by the lambda. So everything in the lambda here that is not either a parameter or a local variable, in our case that's exactly text field, needs to get captured by that synthesized class. So actually, I lied here when I said action listener L equals new action listener 1, 2, 3, 4. What really happens is that the text field got passed in as a parameter, and then a boring constructor that I don't have space to write in here says this dot text field equals text field. So that's actually what's happening. So there is a key. There's a trick, so to speak, on how to deal with all of that information, and that is never to think about it. It's an implementation detail. Somehow, the virtual machine makes it so that when this code here runs, that it reaches the right values. It does work. So the compiler and the virtual machine have to somehow cooperate on this. This particular runtime environment uses classes for everything. In other programming languages, one doesn't use classes for everything, and the virtual machine will use some other representation to do this thing. And so it's not really something that we need to worry about too much. When using this, you simply get used to the way the lambda expressions work, and you say useless parameter coming in, arrow, that's just the syntax, and then the action that you want, and you can touch absolutely anything in here that you want, with one exception. There's a technical exception that says that if you want to, in this code here, reach or update any variables from the outside that are local variables, those local variables must either be final, and you notice that this one here is actually declared as final, because I had, maybe for clarity, or they must be effectively final. A variable is effectively final if the code still compiles when you leave out the final. That's really just about the right definition. So I'm taking out the word final, it still compiles, so that it was effectively final. Meaning no one ever changed text here. 99% of your local variables that you use for references are going to be effectively final. It's pretty rare that you're going to change what hello button is, or what text field is, or what goodbye button, or what frame is. And so you can access all of those things with impunity. Once in a while, you run into a situation where you actually want to change some integer. Maybe you want to update a click count or some such thing. And then the remedy is to turn that thing from a local variable to an instance variable of the enclosing class. You can always touch instance variables. Yes? What's that? You can use this. When you use this inside here, what it means is this of the class that surrounds it. In this particular instance, you cannot use this. Why? No. When you use this in here, then you know that then it refers to the this of the surrounding class. The reason for that is we'll take the point of view that a lambda expression is just some code. A lambda expression happens to be implemented by synthesizing a class, but that's an implementation detail. So a lambda expression by itself has no this. So if you use the four-letter word THIS in here, it must mean that this from the surrounding class. The only reason that you can't use this in here is a little bit subtle. So why can't I over here say like, say this dot text here? So I'm getting a remark here right now.
We should add action master dot this.
That would work either. For a very simple reason. Yes.
Does the lambda expression
No.
like put it out of scope?
No. No. It's a much stupider reason. It's a six-letter word reason. It's a, I can't think that I didn't think of that reason. Yeah. Yeah. You're inside a static method. There is no this in a static method. If this method had not been static, there would have perfectly well been a this, and then your next argument would have been correct that text field was a local variable. But it doesn't even get to that point because it's a static. So it's pretty unusual to reference this inside the lambda expression, but if you're inside a non-static method, you could perfectly well. Yeah.
Was there an anonymous class to implement the action listener?
Yeah. So if you had the benefit of a Java course before, you would have learned something about anonymous classes. So I bring you great news. You can forget about it. So in 99% of the cases, an anonymous class is a class with a single method, and you can just use a lambda.
But where's the implement of the action listener? I didn't see it.
You don't get it. It's made by the compiler on your behalf. It makes it. And you don't even want to know about that. What you really want to know is that the compiler makes it so that somehow this thing receives an object whose one abstract method does the right thing. Don't worry about it. I mean, the thing is, whenever a new feature appears in the horizon, everyone wants to know exactly how does this work. But with things that you've been using like forever, no one ever cares. Like what happens when you call a method? All the parameters get pushed on the runtime stack. The return address gets pushed on the runtime stack. The program counter gets initialized with the starting address of the method. Do you ever think about those steps when you call a method? And what I've told you is not even true. Because half the time, the virtual machine, if the method is short, will inline the method. So when you call a familiar feature, you're perfectly happy to let the compiler and the virtual machine collaborate to just give you the illusion as if the thing that you see is actually happening. And so with these things, it's the same thing. Just trust the compiler. It'll do the right thing to make sure that when this button gets clicked, that this piece of code happens. So yes, you do kind of want to have an understanding of what goes on behind the scenes. But you also want to have that understanding only a couple of times so that from then on, your mental load can be freed from that and you can start being productive and just writing code. So you want to put
Because the previous implementation shows the observers back here, but this is so.
well, it's just like what I used to have when I was a student. I had a part-time job working for this company that did computer games on the Apple II. No one can take that away from me. And so I would complain to my boss and say, why can't we use a debugger? And he said, real programmers don't use a debugger. They use the hex dump. That's what he did. Every time something went wrong, he dumped the entire state of memory in hex, and he just read it and said, oh, there is a mistake. I didn't have time for that. I bought a debugger with my own money. So, at some point, you progress in life by being able to build upon these abstractions. So yes, you once want to know how this abstraction was built, and from then on, you want to just use it. So now that you know how it was built, you go on and just use it, and every time say thank you, that you don't have to construct an object anymore. No one ever wanted to construct these objects.
And remember from, I took 49J, which is your
Yes.
introduction to Java. Doing this was a real pain.
It was a real pain, yes.
Anonymous
Yes.
declaration.
And so hopefully, all of you have not had to learn that before. Don't even go there. It was not better.
That thing is like you, maybe one action, one implement, you want to use it for many places, and then you have
Oh.
to copy the code everywhere. So
No. Then what you do is you say, let me just type it in here. So let's say that for whatever reason you have this action here a lot. Oh, you know what? I have an example for that. I can speak even better. So over here I say, sometimes I want to use almost the same action. I sometimes want to say hello, and sometimes I want to say goodbye. And so then I'm making myself here a little factory method. See over here, where this method here creates a greeting button, or it just creates the listener here, that gets the message here as a string. And it calls text field set text on that message, whatever that message may be. And now it returns this lambda expression. What it actually returns is, of course, an action listener, because the lambda expression is not something I can express in Java. And this way I can call it, as you see over here, by saying create greeting button listener with good button. So I can make as many instances of this listener as I want. And in fact, what happens behind the scenes is now a single class is created with a constructor that has this, and by the way, this has a construction parameter. So I'm not creating infinitely many classes here, I'm creating one class. So the only time that you would ever want to use an anonymous class is if you have an interface with more than one method. So if I go back my 20 years of Java programming, I think that happened to me around 7 times. Maybe 8. But it just is not something that very often happens. So you want to instinctively say, if you need to implement any kind of an interface, there's a good chance it's a functional interface, and you just want to use the lambda expression. It's the way to do it. And pretty soon it'll become second nature. It'll be easier for those of you who have never seen anything else. All right, so we did this. Timers. So we're going to be doing homework with timers, so I have to briefly explain to you timers. Timers are kind of like buttons, except they get clicked automatically. So the way you do a timer is that you have an action listener that contains the timer action. And then you construct the timer object, and you give it how many times per second you want the time. Sorry, how many milliseconds between the timer. So you would have it call once a second. And then you say, call this listener. Of course, you could simply put the lambda expression right inside here, and then you can dispense with the line over here. So let's just look at the sample program that makes it easier. Yep. So here my action listener says I want to set the text to instant out of toString. So that's the current time. When I run this, so over here you see my little atomic clock here, and every second you see it gets updated. You can see it doesn't get updated exactly every second. You can see that because the milliseconds, they've drifted a little bit. So the timer makes a good effort to call you about ever so often, but you can't totally rely on it. That'll be important for the homework, actually, so keep that going. So if I wanted to write this program with a bit less code, then what I could have done is take this thing here and simply paste it here where the listener is. Oh yeah, that may. Thanks. So now I'm saying is, make myself a timer that has this delay, and each time that the timer tick happens, execute this code. So can I make it even shorter? Well, of course I can make it shorter. But did I really need this named constant? I mean, who uses named constant these days? We just put the numbers. Real programmers. So, here, that's short. Can I make it even shorter? Aha! Well, I still need the object. There's nothing to do with that, but I don't need the variable. Right? So, yeah, so I can eliminate that. Oh, I don't. Sorry. And so then I just call start. And oh, I don't need the semicolon either. That's a win. All right. So here it is, right? I'm making a new timer. Ticks every 1,000 milliseconds. Add each tick to that, and get on. So I'm not advocating that you necessarily try to make the shortest expression, but shorter, within reason, shorter is good. All right, so that's how you do timers. Again, notice that timers are almost like buttons, and I think of a timer as a button that just clicks on by itself. Use the same action listener interface, you put the action in there. It's not something difficult. And actually, that is an advantage of Swing. It's very uniform in this way. All right, next. We're going to be drawing a bunch of shapes. In fact, as a motivational example, or scary example maybe, I will show you the homework. So this is homework 5. And so the thing that you're going to draw is this stopwatch. Here it is. And I copied this out from some Wikipedia article where they have the exact same stopwatch. So you notice the stopwatch is made out of several hundred shapes. All of these little lines here. And so you'll be keenly interested in knowing how to do shapes. So for right now, we're going to be drawing all of our shapes in a paint icon method, just because. There's other ways that you'll see later on how we can do them inside a J component, but right now we'll stick with paint icon because that's what we know from the beginning of the chapter. Paint icon gets a object of type component that you can ignore. That's the component that's drawn over, and we don't care about that. It gets what's called a graphics context. Graphics is a thing that knows how to draw various shapes. For historical reasons, there was an old style graphics and a new style graphics called graphics 2D. In the last 15 years, you were always past the graphics 2D, so you can just cast this thing to graphics 2D. Why did they not give you a graphics 2D in the first place? Why did they not, when Java 1.2 came into being, I think 17 years ago, change this method? Because all 973 Java programmers who existed at the time would have had to learn something new. And so it's much better to let 100 million people who come afterwards learn something So that's unfortunately often the way it goes when these interfaces grow. Just deal with it. You get a graphics, you have to make the graphics 2D. Excellent. Graphics 2D is nice. It has a lot of methods. In particular, it has one very powerful method called draw. And you give it any old shape, where shape is an interface, then it just draws that shape. So now all you have to know is what shapes can I put in here. So for a rectangle, you make a rectangle by saying, draw a new rectangle, just pretend that there was a new rectangle, and then it gives the x, y, width, and height coordinates. Except by another historical accident, that's not how you say it. A rectangle, you can't just say new rectangle, you have to say new rectangle 2D.double. This is dumb. I know it's dumb. What happened at the time is people were very concerned, and people just who do graphics are still kind of concerned, that double is a huge waste. Double is what, 8 bytes of data, and has so many digits that on a visual system, whether it's a screen or even the best quality printer, about half of it is completely wasted because it's less than the wavelength of visible light. And so if you have 2 pixels that are so close to each other that the difference is less than the wavelength of visible light, for a visual system, there's no perceptible difference. And so you might as well just use float. So internally, every graphics hardware uses float. So for some reason, someone said, well, what if I have a drawing that has 10 million rectangles on it? In that case, I'm now wasting for width, height, x, and y, 40 million times 4 bytes for those doubles instead of the floats. And so they said, well, doubles are more convenient because the Java floats are a bit of a pain. You have to put an F behind it. You have to cast all the time. But what if that's what you want? So they say, we'll give you the choices. And so if you want floats, you just make a rectangle 2D of float. If you want doubles, you make a rectangle 2D of double. Unfortunately, they didn't make one of these choices easy. I would have voted to make the double choice easy and the float choice the pain. But they made both of them a pain, and so you have to remember to do the 2D.double behind a whole bunch of classes. So you'll see here, ellipse 2D.double. And there's a line 2D.double, and a point 2D.double. It's just like, that's what auto completion is.
And the other one's a rectangle 2D.float?
Yes, absolutely, which we never use. So,
Even though it's more efficient.
but if you want to, if you want to know why we're not using float, try this on your homework assignment. After you're all done, change all the .double to .float, and then see how many casts you need to insert. Because every time that you take 2 floats and you add them to each other, the result is a double. Because that's how Java works. Java promotes all floats to doubles in all computations. So if you want to have it as a float, you have to put cast float around it. And so you would litter your code with all sorts of casts to float, and it's just not working. And Java is not totally crazy in doing that, because the internal hardware, your coprocessor, these days it's on the CPU, right? So the CPU, when it does floating point computations, doesn't use floats. You would really slow it down by always using floats. Floats are slow. Internally, it actually uses an extended double. So you have this mismatch that the CPU wants to use doubles and the graphics hardware wants to use floats. And that's the way. We don't care. We just use doubles and we live with the .double prefix there. I mean, you soon will no longer see. So that's rectangles and ellipses. Oh, for ellipses, there's a bit of a thing that always throws one off the first time. When you specify ellipse, you would think that from a mathematical point of view, you specify the center, major axis, minor axis, but that's not how it's done. Why? Because some other graphics library 50 years ago didn't do it that way. What one instead does is you specify the bounding box. You have to specify the top left corner and then the width and the height. So if you actually want to draw a circle where this is the center and this is the radius, then you have to take this point, subtract the radius, take this point, subtract the radius. That gives you the point over here. Add twice the radius here, twice the radius there, and that's your bounding box, and that constructs your ellipse. One gets used to it, so yes.
Does it enable rotation?
There is a way to rotate, and you'll actually will ask yourself that question somewhere on Sunday, but it's not easy. We're not going to get into it, but maybe we'll get into dimensions.
I was just
Yeah.
curious.
So what you have to do is you have to add the rotation to the graphics context. You can't rotate the ellipse by itself. So all ellipses that you can construct have the major and the minor axis parallel to the coordinate axis. So why do I say you will have that question? That's here. Why do I have that homework? You will ask yourself that question because if you look very carefully at this triangle up here, notice that as this thing here sweeps over, it does have to rotate. And so you will rediscover your trigonometry skill. So there is a point 2D dot double class, and there's a line 2D dot double that joins two point 2D dot doubles that you use for drawing lines. You will be using that extensively in the homework because there are lots of lines. All right, so so here you just see that there's a shape interface. There's a whole bunch of classes that implement shape. Have a look at the shape interface sometime, and you will see that implementing your own shape is not for the faint of heart. It's a very weird low-level interface with like 9 methods, and maybe if I feel exceptionally cruel, I'll make you implement the shape. But it really is tedious. To draw text, I'll just show you this picture so that you understand the problem that you always have with text. Is when you draw text with drawstring, the text is put at the base point, meaning that imaginary line where like all the uppercase letters and all the lowercase letters that don't have descenders on. Notice the G here has a thing that goes further down. You're going to find that a bit painful in the homework because you have to arrange these numbers, so that's 5, 10, 15, 20, and so on, in a reasonable way, and it makes it harder to do that. I've given you a tip on how you can bypass that by sticking the entire text into a label and measuring the extent of the label. So ponder that when your mind is ready for that. Filling shapes, remember that G2.draw draws a shape. When you call G2.fill, then it fills the shape with whatever your current color is. You can set the color by calling G2.setColor, and there's a bunch of predefined color objects. Right now, all we need is color.red and color.magenta and color.black. So at home you can look at this program that draws, this beautiful little car here, and you can see how that's put together. And it's obviously, it's a rectangle with a color, it's a bunch of lines with color. And here you see the 2 circles, and then you see a bunch of text. And these are all response to G2, to the graphics context. So now when you have a car and you draw it, then you notice that the car is not moving. Right, it does, right? So how do we make it move? So that's what I'm going to spend on the next few minutes. And why do I care? Because in the homework, you're going to make the stopwatch move. You're going to set a timer, and you're going to make it so that the second and the minute hand do move in real time. After someone, the top and second come from the Wikipedia description. They talk about a top button and a second button. And the way a stopwatch works is you click on the top button and it starts measuring, and then you click on it again, then it stops. But there is this weird feature that if you click on the second button while it's running, then it freezes the display. I don't know how they do that with the mechanics. It freezes the display so you can see what has been happening, but it continues running. And then when you click the second one again, then it picks up
Where it should have been.
where it should have been, yeah. That's apparently how an actual stopwatch works. I haven't had one in my hands for 20 years, but Wikipedia never lies. So, so that's what you're going to have to implement. And so there you're going to have to deal with how do you make something move. So let's see how we're going to make something move. So, obviously, we're going to be using the timer in some way, and we're going to be doing it in the most primitive form imaginable. That once a second or 10 times a second or whatever, the timer, when it gets an event, it's going to tell this thing here and say, hey, move, 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 move. And each time, the expectation is that the car is going to move over a little bit. Well, how's that going to happen? So really, what does a car know? A car knows how to draw itself because it knows how to draw the body and the wheels and that kind of stuff. So that's one of the things it knows. Now, if one gives the car a position, like an XY from which it starts drawing, right now the XY is here, then all Move has to do is increment it a little bit, and then the next drawing will move it a little bit further to the side. So if in the draw code we make it so that all drawing is relative to some initial position, then you only need to update that. So let me show you the code for that. So here's my car, and so you can see the car stores its top left corner. Also, I make the car so that you can have cars of different size, so that you can have a bigger car than the neighbor, and so then you just need to construct it with a bigger width. There you go. What's that?
For every power source generator relative to the width.
Well, these shapes here, these car shapes here, you draw them completely from scratch.
Right.
So it's up to you to do what you want to do. But it's a really good idea to always remember in top left corner. And then when we look at the drawing code, it does make the drawing code a little bit more complicated because a lot of times you have to add the x and the y to everything. So you see here there's an x plus y plus, x plus y plus, x plus y plus. So every single computation is offset by x and y. The way that I figure this stuff out is I take some graph paper and I start as if my car was at 0, 0. And then I figure out the coordinates. 20, 40, 60. And then I figure out that I need to go from this one, 20, 40, 60, something like that. And then then I say, okay, so it looks like this thing here is my width. In my example, it is 60. So each time what I do is I compute. I don't have any idea why it's over 6 here. Oh yeah, I do because when I did my first example, I said, how do I need to do this wheel? This corner here is 50, 40. This length is 10. And the height is also 10. That's how I must figure it out. Then I say, well, but that's not the world I'm living in. I'm living in a world where 10 pixels are actually width over 6. And so that's where every time that I had 10 in here, I put in width over 6. Every time that I had a 20 in my calculations, I put a width over 3, and so on. And also then I offset by x and y because I'm not starting at 0, 0, but I'm starting at some arbitrary x, y, and that's where you see all of these offsets in. So when you do this thing for the for this thing with all of these various tick marks, it's a really good idea to first set the origin to 0, which means that you won't be seeing anything but one quadrant, but that's good enough for testing. And making sure that you have everything positioned right, and then you just add x, y to it. It's hard to do it otherwise. If you've done it often enough, you can do it in your head, but otherwise, you're better off first getting it to work with some concrete thing. And I didn't get it to work with a radius of 100 or something. Maybe 100 is a little small, because you can't see over 500 or something. And then scale it up. All right, so the drawing has this feature that it can draw the car no matter what the starting x and y are, and it'll draw everything offset by x and y. So now the move method is very simple. It just increments the x. So each time one calls move, it sets x one further. Then, of course, draw needs to be called again so that it draws it again at the new position. That code is here in this animation tester, which is what you're going to be getting for the homework in almost the same form, except with a stopwatch and not a car. And here is what the timer does. It tells the car, the shape of the car, to move itself. To take move. And then we need to redraw the car. There is a technical problem here with the redrawing, and that is that I cannot simply call shape.draw. I'd like to do that, but I can't. Why not? There's a much more trivial reason. Like the compiler would not let me do this. And you may not remember because you've just looked at this code for a very short amount of time. But let me show you the car again. Here's the draw method. So, like I said, what I wanted to do is call shape.draw. So why can't I call it? Yeah, it took a parameter. It took a parameter of type graphics 2D. So I would have to pass in a graphics 2D. How do I get a graphics 2D? Weirdly enough, there is no way you're legally going to be able to get one. Now, you could go under a bridge somewhere and see if there's a fellow with a trench coat saying, any graphics 2D? But no, you can't get a graphics 2D. The only ones who know how to make a graphics 2D is the graphics subsystem that we don't really have any access to. So all I can say is I can say I want the, where was it? I can tell the label, could you please repaint yourself? And then the label will register a request with the graphics subsystem that says, can you repaint me? And then the graphics subsystem, when it's good and ready, will do the repainting. The graphics subsystem tries not to do unnecessary repainting. So when it's busy with other things, it'll actually defer painting until later and coalesce adjacent paint events so that painting is done as little as possible. Painting is expensive. So that's our indirect way of calling draw. And then draw will be called on our bit we have in all the time. So that's fine. So this is how we get the moving effect. We move the object, we repaint it. Move, repaint, and that way it'll slowly slide over the screen. Did I show this? I mean, it is truly uninspiring. So. Here it is. Right, it's amazing. Yeah, this was cool stuff around 1997. So, anyway. So the point that I now want to make is that if you look at what this loop did, the drawing and the moving, that had nothing to do with the car. You can do that with anything that you want to have moved around. And so when you have a mechanism that has nothing to do with the specific instance, this is a good time to say, hey, opportunity for an interface. The animation code that you saw, the one that sets up a timer and all of that good stuff, will work with anything that one can draw and move. So we're just going to make an interface for stuff that one can draw and move, and I call it a movable shape. And skip the CFC card, and here it is, a brand new interface, never before seen by man. So actually, it has been seen before in the old edition of the book. I made it slightly differently, and then it didn't work for the stopwatch, so I changed it. If you downloaded the code or you downloaded the PDF, please re-download them to get this latest. So, the movable shape can draw and move. The car shape, oops, and here you can still see the little one. This should say move. I'll fix this right there. The move will just do the increment here, and draw will do whatever it is. What you're going to do for your homework is you're going to be doing the stopwatch that implements movable shape. Now, with a stopwatch, what I mean with moving is not that the stopwatch moves from the left to the right. All I mean is that the hands move. Okay, so you're going to update the hands to their most current position. All right, so I want to end this by showing this nifty class here. Well, there's one more thing that I need to show you. And that is, I made a little adapter to deal with the following technical issue. When you look at the car has a draw method because the car knows how to redraw itself, and it gets the graphics 2D. But later I need to put a car into a label. That's the only way that we know right now on how to draw anything. You put it as an icon into a label. And this is a movable shape, and it's not an icon. An icon is a different interface that has 3 methods, and this just happens not to be one of them. So I made an adapter that I call shape icon that takes a movable shape and the width and the height and turns it into an icon. So this thing here implements icon. And all it does is it makes that cumbersome paint icon method with a component in this X and Y. It makes it call draw on the underlying shape. That's all. You're going to be using that in the assignment. It's just an adapter. Yeah.
Could you have also possibly extended icon?
I could have done that. But I thought it was a bother to have this get icon width, get icon height. I hate that interface anyway. I only used it because it's there. And it's a kind of a useful technique to build these adapters when you have something that conforms to one interface and you need to like translate it over to another interface. In fact, we're going to at one point be talking about what's called the adapter pattern. So that was my other motivation, to sneak that into here. So right now it's just a way that you can smuggle a movable shape into a label by wrapping that in there. All right, so you will be keenly motivated to study this code because your homework is based on it. Undoubtedly, you will be having some questions because there's some of the drawing operations that I did not tell you how to do, like that triangle there. And so I'm just waiting for the Piazza question that says, I can't find a triangle class, because then it'll be time for a hollow laugh on my side. There is no such class. And so you're going to have to figure out some other way. I've given you a pointer that you will probably find obscure. In that case, ask questions on Piazza. So it's perfectly fine if you discuss with each other how to render these drawings. You learn something by reading the documentation about that. If you can't figure it out, I will, of course, tell you. Okay, well, happy coding over the weekend.